In this short video, we are going to give an introduction to the fascinating topic of software-defined networking, which is currently widely entertained in the networking community, and I think is underappreciated in the distributed computing community. So there is a universal tendency. Whenever you have difficult stuff to deal with, you delegate it to the experts. For example, if you have some massive content, you send it to the content distribution networks. When you have a lot of computation to perform, you delegate it to the clouds. When you have to deal with concurrent programming, you try to use transactional memory, which was carefully crafted and prepared in advance by experts in concurrent programming, so that make your life easier. What about network management, which is notorious for being difficult, best effort, unreliable, and so on? So how can we simplify it and make it tractable? So the idea is to delegate it to carefully prepared and crafted network control application. Before we discuss the concept of SDN, let's recall how the contemporary networks are built. Currently, it's actually pieces of hardware, switches or routers, which connect the users, allow them to communicate, access some data in remote places. And at the moment, every piece of hardware in the network performs two parallel tasks. First of all, every piece of hardware participates in the data plane, involved in forwarding of data between the users. And also it is involved in the distributed control plane that deals with all the features of networking not directly related to forwarding, but enabling forwarding, such as routing, access control, monitoring, etc. So nowadays, network management features such as routing, building paths between users and data, and between users and users, monitoring, collecting statistics about the network state, network behavior, failures, access control, making sure that certain data doesn't reach certain destinations, etc. All these features are currently implemented in a distributed way. So these are distributed algorithms that run on top of the data plane on the same hardware, and they are inherently best effort. They don't provide any guarantees whatsoever, except that if the network is stable and no failures occur, the protocols perform the tasks they are supposed to. The fact that they are distributed and best effort makes it hard to deal with. So the networks nowadays are hard to manage. They're hard to innovate. It's very difficult to introduce new useful features. And respectively, since they are hard to innovate, they are also hard to provide any quality of service guarantees. It is common to say nowadays that the expectations from those networks, especially for most of the computing tasks we now perform, we use networks, and the expectations from the networks are much higher than the guarantees the network can provide. The idea of software-defined networking is to separate physically the data plane from the control plane. So the control features, control applications of the network would be delegated to a physically separated control plane. So this would involve monitoring, forwarding, security, access control, etc. It's important to guarantee that in some sense the control plane can be seen as a logically centralized entity. The control plane would be just involved in forwarding data between users of the network and would consist of a collection of simple but efficient network switches, which we call SDN switches. While the logically centralized control plane consists of SDN servers that would implement all the network management logic our network needs to maintain. And of course, we need some standard interface between the control plane and the data plane, and that will be implemented using some standard API. And one of the recent proposals to use it is a standard open flow protocol, which describes both the configuration of the switches and the interface between the switches and the servers. It's also important to notice that while the data plane is currently large scale, so currently it may be billions of hosts, the control plane is orders of magnitude smaller. So it should have a small number, maybe thousands of servers, just to make the network control tractable. So in OpenFlow, data plane is programmed using rules. So rule is just a pair of condition and action. So when the condition on the traffic on the network packet is satisfied, a certain action should be performed, and the switches on the data plane are programmed using OpenFlow forwarding tables, which are just collections of rules with different priorities possibly. One example of a rule could be like a rule with priority 30, such that if whenever you have received a packet with TCP destination port 22, so it's an SSH TCP packet, so you would simply drop it. This would be a rule. And then a collection of rules installed at different places in the network and different switches would create a policy. An example of a policy would be, for example, saying that forward HTTP traffic from X to Y. For example, if I have host X, host Y, and I receive an HTTP traffic, I would forward it to Y, and that would configuration changes on multiple switches, so that's why I need to update some rules. So therefore, an SDN system can be seen as an extended network, which is a data plane equipped with management tools, which are presumably easy to use. It's also a resource management that arbitrates the use of the network between different control applications, such as routing, load balancing, monitoring, etc. So in a sense, this looks like an operating system, but a network operating system which deals with data communication. So as a network operating system, it deals with abstractions and resources. What are those abstractions and resources? So first of all, it deals with data structures which describe the network as a whole. This could be topology of the network, load distribution, etc. It should also give an abstraction of an update of the network. So since the network, the data plane is inherently distributed, we have to deal with a distributed update. For example, when we need to install a new policy, this would incur changes in the multiple switches on the data plane, and they cannot be in one atomic step, so that it is inherently distributed. We need to do it by preserving some high-level consistency of the network-wide structures which we have. One important feature of modern network is the ability of virtualization. So virtual network is another important abstraction which we need to maintain. And another important thing is the ability to compose different control modules in a transparent way. Especially it is difficult if you have ongoing traffic on the network. So the idea of SDN would be then to make network management tractable, enable seamless innovation, which we seem to be needing for forthcoming applications, which require more and more resources from the network and more quality of service, and we provide this quality of service. Is it really so easy? I would argue that there are some inherent difficulties in implementing this strategy. These difficulties relate to the fact that the implementation of an SDN control plane should be resilient. It is unlikely that you would like to run all your control applications on a single server, so you need to produce some replication and so on. But at the same time, it should provide some kind of synchronization among control models. And as we know, these two concepts in computing do not go very well together. And I will give a couple of examples to illustrate what is special in the domain of software-defined networking with respect to resilience in synchronization. So let's suppose we have a network, and the network looks like this. We have a bunch of switches, 2 users here. Possibly we also have a link here, and there is a route from one user to another going to through the shortcut link. And let's suppose at some point this link goes down. And now it is the task of the control plane to find a new route. And let's suppose for resilience we have 2 SDN switches on the control plane that are not perfectly synchronized. And then they also try to implement a new route based on the network statistics they collect, and they may have different moments of time, they can collect different statistics, and according to the first switch, the currently available less loaded route is the following one. According to the second one, the better route is this. As you can see, if the 2 servers try to install these 2 routes concurrently, you may have a temporary forwarding loop on the data plane. Many people believe that it's not good to have such loops because you immediately exceed link capacities and you have a lot of pathological effects which you try to avoid normally. That is why, in the absence of synchronization among the SDN servers, trying to do some good things for a good cause, you may get some pathological effects, and it is up to the programmer of the control plane to make sure that this never happens. Especially in the presence of the traffic, because an incomplete update may start affecting the traffic, and sometimes you also try to avoid this. I'll give you a different example of a conflict among control modules. Let's consider a network of 3 switches. Let's suppose we have 2 concurrent modules on the control plane. So one module is involved in routing, forwarding of data. The other module is involved in monitoring. And let's assume that they try to implement two different policies. Of course, the forwarding module would try to implement a forwarding policy and build a route between the two users, for example, and the monitoring module would try to collect statistics from certain nodes on certain types of traffic. For example, the forwarding tries to install the policy which says forward all HTTP traffic to Y. The monitoring module would try to install the policy which would simply count all packets coming from X. So when these two policies are being installed on the switches, the data plane, potentially we have a problem if we have a packet with the web traffic coming from X. We have two actions concerning the same type of traffic. The natural answer here is to compose the rules. Here we need to understand some semantics of composition. Well, natural semantics of composition is to make sure that the traffic is forwarded and counted at the same time, and this requires some kind of composition rules, so it should be installed on the control plane in the first place. Let's come to the example of two forwarding modules now. And let's suppose that the second forwarding module is trying to forward all traffic from X to user Z. And again, the question is what to do. HTTP traffic from X is not so easy to answer. Typically, you would say that in this case, the two policies proposed by different control modules do not compose. So composition is a problem which must be solved by the control plane. And again, this kind of problems may be difficult to address in the presence of ongoing traffic. So the idea of software-defined networking is to make network control tractable by providing network abstractions, modular composition of network control modules, network virtualization, distributed updates, etc. But implementing all these nice features is challenging, and in particular, to ensure a certain level of quality of service and consistency guarantees, we need to resolve some novel problems of resilience and synchronization, which is a very interesting topic in itself. As a side remark, I would like to mention our forthcoming InfoCom paper, which talks about transactional SDN control plane. And the idea here is to implement operations on the data plane performed by software modules of the control plane as transactions with guarantees which are similar to database transactions, sort of all or nothing, because the presence of ongoing traffic and ongoing changes in the statistics of the network do not allow us to define these transactions in a perfect atomic way. But still, it is much better than what we had before, where networks were operating in a best of way. And this way, since we know that transactions are conceptually very easy to deal with, they compose, or at least semantically they are very easy to be composed. They can be implemented in an efficient, comparatively efficient way. They allow for consistent perspectives of network-wide structures like topology and overall network load and so on. So it has a number of nice features. So this could be a nice way to address resilience and synchronization features of modern SDN networks.